Hey, in the last video we discussed how computers can add two numbers together. In this video, we need to expand upon that and talk a little further about the computer that we're building. The computer that I'm explaining in this video is somewhat of a retro approach. However, we're using some modern ideas to help us solve some older solutions. With that in mind, remember that all computers are designed with a specific purpose. The computer that I'm designing's purpose will not to be able to play the new and upcoming GTA 6. And I'm sorry if that was your goal, however, almost everything still applies to modern gaming computers anyway, just at a larger scale. Just think that instead of GTA 6, we scale down to maybe something like Zelda. No, not that one either, I mean classic Zelda. Something that sets this computer apart is that its CPU is very simple. It is a single core CPU. This basically means that it can only do approximately one instruction per clock cycle. Another thing that is, it will not have a graphics card. This doesn't mean that it can't play games or have a monitor, it just means that it will utilize onboard video processing instead. Anyway, before we can get into that, we need to learn a little bit more than just adding two numbers together. But before we can continue, I have an important question for you. Do you need a PCB? Well, there's no better way to get one than with our sponsor, Ivon. If you're looking for a quality PCB, there's no better place to get it. Do you need just one board? They can do that. Well, what about 10,000 boards? They can do that too. Not only that, but they make sure that every board works. Every board at Ivon is inspected and undergoes rigorous stress testing to ensure that you get the quality that you deserve. Bring your PCB ideas to life with Ivon. If you would like to purchase a PCB, please make sure to use my creator link in the description below. Thank you, Ivon, for being the sponsor of this video. Okay, so how exactly can we make our computer do more than just add two numbers together? Right now, with just the knowledge of the adder and the basic logic gates, we're kind of stuck. Our computer can only add two numbers and that's it. It's pretty boring. Let's give our computer the option to be able to select from two different options. We can do this by using this simple circuit called the multiplexer, or MUX for short. The multiplexer lets us pick which data we would like to use in a location. In this case, we can select between two 4-bit numbers. These numbers can come from anywhere. For now, both of these numbers are manual entries. Let's say that number 1 here is 10 and number 2 is 3. Easy enough, we see the output over here as 10. This is because the multiplexer's job is to always output one of these numbers. By default, it will output the first number unless the selector bit is turned on. If it is on, then we can see that the output shifts to number 3. You can visualize this like it's the trolley problem, except nothing bad is going to happen, of course. But the train has to go down one of these paths. To change the path, we just flip the switch, or the lever. However, in this case, the lever is a binary 1 or a 0, and the train is one binary data bit. By default, if the lever is 0, the train will go straight. If it is a 1, then it will take the other path. This is important because computers couldn't necessarily do more than one task without this. Do I only want to add two numbers and then reset the computer? Super boring. To solve this, we can actually add a different path. Let's say that in this case, we're going between adding and the logical path of AND. Something important is that we have a single little multiplexer. The way that this works in its current state is that it lets one little bit through at a time. I would like to let 16 bits through instead. To do this, we can combine 16 multiplexers together and tie the selector bits together. So that way I can shift 16 bits of data with only one pin. This is now a MUX 16. At this point, we now have two instruction options, add and bitwise AND. To select between the two, we just turn on this MUX 16 switch bit. When designing a CPU, you can name things. I'm going to name this MUX 16 to F for function. At this point, we should have a pretty decent understanding on how a multiplexer works. Okay, I want you to think about this. How do you think computers do subtraction? Before learning about this, I thought computers did subtraction the exact same way we did. Something like this. 5 minus 3 equals 2, where 5 is 0, 1, 0, 1, and 3 is 0, 0, 1, 1. We end up with 0, 0, 1, 0, which is 2. Well, oddly enough, computers do not think this way because it's kind of inefficient. I would like to introduce you to a new concept, 5 plus -3. Okay, maybe it isn't too different, but this method still yields the same result of 2. If you hadn't noticed, we're adding 5 and -3. A few things are cool about this. First, -3 plus 5 is still 2, so order doesn't really matter. Second, we do not have to make a new instruction for this. If we can figure out how to make 3 a negative number, we can just use what we already have and just add the two numbers together like we have been. So how exactly do we turn 3 into a negative number? There are many solutions to this problem and they all have their own drawbacks, but this is how we're going to handle this. First, let's start with a 4-bit number. We have 0011, which is 3. If we want this to be negative, we must alter the data somehow. If we're operating off of a 4-bit system, we probably do not want to add any more bits to this, otherwise we end up with something that our CPU may not be able to understand. We're going to use this leftmost bit here to assign a negative number. This leftmost bit, the most significant bit. If this bit is a 1, we have a negative number. If it is a 0, then we have a positive number. In this case, we now have 1011. We can now visualize this as -3. So let's try and add -3 and 5. Well, that doesn't really quite work out so well. We're left with the number 16, and since we're using a 4-bit system, 16 is non-existent, so we're left with 0. If my basic math skills serve me correctly, 5 minus 3 is not 0, so we need to make some tweaks to this system. Let's look at things this way. Let's draw out all of our current possible combinations of bits. Okay, so looking at this, we're supposed to have 16 combinations. We do in fact have 16, but 2 of them are 0 and -0. I don't ever really remember learning about -0 in math class, so let's instead start with 1000 as -1, so that way we no longer have -0. Now this looks a little bit better, a true 16 possible combinations. I'm going to spare you a few minutes of binary math and tell you that this still unfortunately doesn't work. If we do the math with this new number, we in fact end up with -8 with this current method. This actually brings us a little bit closer. What if the solution is not? Okay, that may sound a little misleading. Bitwise not. What if we just invert all of the bits except for the most significant bit and we keep that number as -3? And if we do the math, it actually seemed to have worked. Now that was a lot of steps, and they really were quite out of order, and it really gets more simple once I explain this. So how can a computer do this? Well, step 1 is you take the number, and you just invert it. Step 2 is you add 1 to the number, and step 3 is just adding the numbers together. It may be a little difficult to understand this now, as the bigger the binary number, the smaller it actually is. This way of handling negative numbers is what we call 2's complement. Now it is officially time to put everything together. We understand how computers handle negative numbers and what a multiplexer is. However, our computer is still boring. We can add negatives, positives, or compare negatives and positives with bitwise AND, that of which is still boring and technically not a computer. So what can we do to make this a little bit more interesting? Well, we can start thinking of more things that we would like our computer to be able to do. For example, instead of giving it a positive and a negative number to subtract, we can instead give it 2 positive numbers and subtract those. That means that we can calculate a negative number and then add them. Eventually, we'll have made enough functions that we have created what is called an arithmetic logic unit, or ALU for short. This is what does the math inside of the CPU. What I find cool is that if we do things efficiently enough, we can end up only using a few previously spoken concepts and end up with many different results. Let's look at it this way. This is what we have right now. In this stage, we can only add x and y, and then we can do bitwise x and y. In its current stage, the ALU is not quite adequate. Let's look at some things that we can do. Also, from this point on, at the end of each segment, I'm going to have a table pop up of the different outputs that we can achieve if we turn on a combination of operation bits. So far, we have only have one bit, and that is F. Remember, this means we can either add the two numbers or compare them with bitwise AND. Alright, so if we have the ability to force the incoming Y input to be 0, then we have the ability to have whatever the incoming X input is as the output. Now you may be asking, how exactly do we force the incoming Y input be a 0 if we turn on this bit? We do use a simple mux circuit. For now, let's visualize this with only one bit. Currently, we have whatever the Y input is, and then whenever I turn on the selector bit, we want to force it to be off no matter what. We simply do this by connecting the B side of the mux directly to ground, aka 0. Remember, whatever is connected to the A input of the mux is automatically being passed through. The second we turn on the selection bit of the mux, we instead pass through whatever is connected to the B input, which in this case is 0. Now, to do this to the entirety of the Y input, we must do this to every bit. Then we connect all of the selector bits together. In the end, we end up with the ability to 0 the entirety of the Y input. Let's go ahead and do this for the X input as well, so that way we can have the same results for the Y input. At this point, we have 3 bits that we can turn on, and it will affect the output of the ALU. Here is the updated table of possible outputs. Believe it or not, we only have 3 more operation bits that we need to add. With every operation bit that we add, we unlock many more possibilities. This next operation that we're looking at is the not Y, or we can also say invert the Y input. Basically, flip every bit to the opposite bit, similar to how the 0Y worked. Instead of connecting the B input of the mux to the ground, we take the Y input and connect it to a not, and then connect that to the B input of the mux. Once we do that to every bit of the Y input, we end up with the ability to invert the Y input. At this point, we have quite a few possibilities, but the biggest thing that we can do with this is we can now do X minus 1. What is neat is that if we 0 the Y input and then invert that, we end up with the -1. What is -1 in binary? It's all ones, aka every bit turned on. Remember, we're using 2's complement for negative numbers. With this in mind, we can just make the Y input -1. If we force X to be 0, then our output can just be -1. Yet again, let's copy this over to the X side, and we can now invert X. This means we can do X minus 1 as well. Alright, so this last bit is what makes the magic happen. All it simply does is invert the final output. So it is the same thing we did with not X and not Y, but to the final output. So what exactly does this do? Just by adding this final bit, we add 10 new outputs. The most important of them is -X, -Y, X plus 1, Y plus 1, X minus Y, and Y minus X. And lastly, bitwise X or Y. Most of these can be visualized pretty simply, but what I do want to focus on is X minus Y. In order to do this operation, we must turn on NX, F, and NO. How does this work? If we have X equals 5 and Y equals 3 in binary, and we want to subtract them, let's look at how the ALU does this. We first invert the X input, so 0, 1, 0, 1 becomes 1, 0, 1, 0, which is -6. We then add these two numbers together, so we end up with 1, 1, 0, 1, which is -3. The last thing that we do is invert this last number, so 1, 1, 0, 1 becomes 0, 0, 1, 0, which is 2. That's the correct answer. If we wanted to do this to Y minus X instead of inverting X, then we just invert the Y input. With this, we have a fully completed ALU, and I'm serious. This is the exact ALU that I have right here. I have a full YouTube video of me testing it, and it works 100% the same as I just described to you. So if you would like to see a fully working version of this, it is titled A Look at My ALU right here on my YouTube channel. Well, I'll say that was pretty productive. I hope that you all enjoyed this video. It was a little bit longer than usual, but honestly, I think that's a good thing. My guess is that the next part of this series will be out either next month or in March. In that video, we'll likely discuss memory. If you have any other ideas or things that you'd like me to cover, I will definitely make a follow-up video explaining that. Well, anyway, I hope you all enjoyed the video. I will see you all in the next one. Bye-bye.